Okay, so chit chat is over. We switch to English now. I want to give a relatively informal talk on current. It's not exactly a work in progress. It's more like a project trying to see where this leads. This is joint work with Joanna Meinel, who is joining us today. And I have to switch this. And it's surrounding some of this Gelfand-Tsetlin stuff, which I have mentioned several times in the seminar. But I am going to give a self-contained talk. I'm not going to make reference to previous talks, maybe in some details. But okay, so I want to insist I will not be telling any new results. I'm just going to say where our thoughts are at the moment and what kind of thing we would expect to obtain at the end and why we got down this road in the first place. Okay. So I want to start by fixing two integers, positive integers. A vector space which is going to be C to the n. All this talk is going to happen over C. All complex vector spaces and everything is going to be over C. And I am going to call G the Lie algebra GLN, which is of course the Lie algebra of the vector space V. V has a canonical basis, which I will denote as usual by E1, E2, En. This is just the usual canonical basis. And I am going to fix a Cartan subalgebra inside G. H is just the diagonal matrices. And a Borel subalgebra, which will be just upper triangular matrices. Okay, so this notation will be in place for the rest of the talk. So I want to recall some very basic facts on the representation theory of GLN. In particular, that if you give me a sequence of numbers like this, lambda 1 less than, bigger than or equal to lambda 2, lambda 3, and so on, these are all integers, non-negative integers, then there is a unique simple highest weight representation, finite dimensional representation of G, which I will denote by V lambda. Right, so this is just a finite dimensional representation of G, and it contains a vector, which will be V, little v lambda, such that when you do this, so if you act by the Cartan, you just get the same vector, and if you act by the Borel, you get the same thing. And strictly upper triangular matrices kill this guy. Okay. So to any such lambda, I can associate its Young diagram. And I'm not going to define what a Young diagram is. I'm just going to show a couple of examples, and I think that should work. So for example, if this sequence has two entries, so n equal to 2, and this lambda is just the sequence 2, 2, its Young diagram is a diagram like this with 2 boxes in the first row and 2 boxes in the second. And if n is 3 and lambda is this sequence 4 to 1, the Young diagram is this guy. Okay, so just a diagram of boxes with lambda 1 boxes in the first row, lambda 2 boxes in the first row, etc. I think we all know about this. Okay, so V as a representation of GLV is one of these guys here. It is the representation associated with the partition 1, 0, 0, 0, 0, 0. Right? In this case, lambda is just 1, 0, 0. Okay, so there's a very nice fact called Peary's rule. That tells you the following. Suppose you have one of these guys, one of these V lambdas, and you tensor it with V, right? So with this guy, with the standard representation of GLN, the defining representation. So Peary's rule says that this decomposes again as a direct sum of these guys, right? Because G is a Lie algebra, so you will just a second, something happened here. Yeah, so you get the tensor product of 2 G modules will be a G module again. It turns out that this is a semi-simple module and it decomposes like this, and I can tell you what the mu's look like. They belong to a set called lambda plus. So this just says that the Young tableau, the Young diagram of mu is the Young diagram of lambda plus 1 more box. Right? And every single mu like that appears here exactly once. So let's do a little example with our with the 2 partitions we saw. If we take this tensor product, then what I have to do is I have to look at this Young diagram and I have to imagine where can I add boxes to it? Well, I can add boxes in 2 places. I can either do it here or I can either do it here, right? So V22 tensor V will decompose as V221. So you can think of this as V220, V221, direct sum B320. Because the Young diagrams of this are obtained by adding exactly 1 box to the diagram of this one. So this gets a bit more complicated as you go on. For example, 421 tensor B will have 4 components. I will just write them down quickly. They are all obtained according to Peary's rule. And this gives you a very nice way of finding decompositions. This is a generalization of Clebsch-Gordan's rules for SL2, which everyone has seen at least once, I think. This is like a much more general rule. But so Clebsch-Gordan is for arbitrary simple representations. This is for the defining representation in particular, but it works for all GLN. And I want to discuss one very nice pattern that arises when you just take successive powers, tensor powers of V with itself, right? So V itself is just this representation. And if I apply Pierre's rule to this, when I want to decompose V tensor V, I get one representation corresponding to this diagram and one representation corresponding to this diagram here. And this is just the usual, the familiar decomposition. This is just the representation corresponding to the symmetric tensors inside V tensor V, and this is the exterior power of V. So antisymmetric tensors in here. And now Pierre's rule will allow me to do this again, to compute the decomposition of the third tensor power of V with itself, because all I have to do is this.
Sorry, Pablo.
Yes.
Why don't we have the summand 4220 in the last example?
Because I forgot writing it.
Okay, thank you.
Yeah, no. Because I made a mistake here. This should be 422.
Okay, thank you.
Yes, thanks. So I'm applying Pierre's rule to find the decomposition of this guy. And then I am going to get, just as usual, I will do this also quickly. I will get this. I get a copy of this 2-1 from this first summand. So this is the first summand. And the second summand will give me something like this. Okay. And so this shows that there's a very special phenomenon, which is that suddenly I have a representation that appears twice in this tensor product, right? So Pierre's rule says tensoring with a simple representation with V will give you a direct sum of simple representations which appear exactly once. But repeated application of Pierre's rule will make copies of the same representation appear in the decomposition. This is a very standard and very well-known fact. And in fact, a classical question that goes back to Weil and Schur and all those very important guys asks how many times does V lambda appear in V to the tensor power D. Right, so this is, in this case, for example, B21 appears twice inside V tensor V tensor V. And it will not appear in any other tensor power because you always have to go adding boxes, right? So when you compute this multiplicity, which is usually denoted like this, you're always assuming that lambda, the parts of lambda, lambda 1, lambda 2, etc., should add up to D. Otherwise, this doesn't make sense. So this is 0 unless the parts of lambda add up to D. So this is written like this. This says that lambda is a bunch of integers that sum up to D. Okay. And the answer to this question is, I think, a very beautiful argument, which says that, a very beautiful fact, proved by a very beautiful argument, that this multiplicity is the number of standard Young tableau of shape lambda, the number of standard Young tableau of shape lambda. And again, I'm not going to define all of this. You probably know this, but I'm going to make an example of how to compute this. So say I want to find the multiplicity of this representation here. I already know it's 2, but I can use this answer to prove it just by showing that there are 2 standard Young tableaux of shape lambda. Right? So the shape has to be this. And a tableau is just a filling of these diagrams with numbers in the boxes. And it's standard if the rows are increasing and the columns are increasing. So this forces me to put a 1 in the top left box. And then there are 2 ways to continue. There's this and there's this. And these are the only 2 standard Young tableaux of shape 2, 1. And this is telling me that the multiplicity has to be 2. And I claim that we know enough to prove this very easily. And the way to do that is the following. You just repeat this process I've been doing here, right? And at each step, when you add a box, thanks to Pierre's rule, you write the number of the step you're in. So for example, here I will write 1 for this box. And when I am doing this tensoring process here, what I am doing is I'm saying, okay, I'm starting with this 1 box and I'm adding a 2 box here and a 2 box here. So now in the next step, this is the tensor I am computing. And so I had these 2 boxes and I just added the third. I had these 2 boxes, this is the one I added. I had these 2 boxes, this is the one I added in this step. I had these 2 boxes, this is the one I added in this step. And by repeated application of the Pierre rule and this idea, you get a proof of this very classical fact, right? That the multiplicity is this. Okay, so we have just proved a very nice theorem, but here's the deal. We have done more than this. We have assigned, we have shown, we have given an assignation that to each standard Young tableau of shape lambda will assign a very specific copy of V lambda inside V tensor D. Right? And the process is just, you just do what I just did and you just check which copy of V lambda will have this, tableau as its sub-index, repeating the argument I just did. And this is a lot stronger than just counting multiplicities. I am saying that for each standard Young tableau, I am getting a very specific subspace in here. Right? I'm saying that it's going to be a V lambda, so its highest weight is lambda. And I'm saying that it's in here, but it's a very specific copy. There are many, many copies of V lambda inside. You know, I could just take as many as this, or I could take like a transversal copy of several and just take the diagonal. There are infinitely many. But there's one that's somehow distinguished by this Pierre process. So you can ask a couple of questions about it. For example, given T, can you find the corresponding subspace Vt without a recursive process? Right, so I want to give you V tensor D, and I don't want to go through all the steps of the decomposition. I just want to know which subspace in there is V sub T. One way of doing that is give me the highest weight vector in here, right? I'm going to call it little v sub t, just like the v lambda was the highest weight of the v lambda. And this would be a bit more than the previous, but they're essentially equivalent up to some Lie theory, up to some computations with the Lie algebra G. And if we are getting really ambitious, can you give me a weight basis of Vt? Now, of course, all of this depends on how I understand vectors in here, right? If I want to, I don't know, automate this, put it inside a computer, I have to have some way of discussing elements of V tensor D. But the whole point is that elements in V tensor D are very easy to discuss. I have a basis of V, which is just the canonical basis. And V tensor D has a monomial basis out of this, right? Which is EI1 tensor EI2, etc. This is a very convenient basis to work with on V tensor D. So in fact, finding these guys and finding a weight basis, these things are not easy to handle if you're just working with abstract versions of the representations. But if you find a nice realization in here, computations become a lot more concrete, and you see a lot more about the representations. Okay, and I want to insist that while I think this is a very natural question, it is doesn't lie very deep inside the theory, right? I'm going to show you that there's a relatively straightforward answer, but surprisingly, it just came up in the last 15 years, something like that. The tools to give a very concrete, very recursion-free answer to this question date from a paper from 2008 by Vershik and Okunkov. And that's going to work for this and for this, but this is going to be, I'm going to discuss the details of that later on. Okay, so now I want to talk a bit about representations of the symmetric group SD, which is what is going to help us answer our question. Okay, so the DF symmetric group has a bunch of irreducible representations. And as for any finite group, irreducible representations of SD are in bijection with conjugacy classes of the symmetric group, which are in turn in bijection with partitions of D, right? Because if you give me lambda 1 to lambda n partitions of D, a partition of D, a sequence of descending integers, I can just form something like this. This is a collection of parentheses, and here I can put lambda 1 numbers from 1 to D, say 1 all the way to lambda 1, then lambda 1 plus 1 all the way to lambda 1 plus lambda 2. This is lambda 2 numbers, and here I will put the last lambda n numbers. This is an element in SD, right? It's just a permutation written in cycle notation. And any element that is conjugate to this one will have this cycles of the same size in the decomposition. And any element which decomposes into cycles of this same size is conjugate to this one. So conjugacy classes are in bijection with lambda. Now, this one here is not purely abstract, right? It's not true that for every group there is a bijection between irreducible representations and conjugacy classes. We just know that there are as many of one as of the other. But for SD, we have a construction that will associate to each lambda, so to each conjugacy class, an irreducible representation. And this is very particular for the symmetric group SD. And I'm just going to quickly recall how to do it. Say that my partition is 4, 2, 1. Then you have to build something that is something like the most standard of standard tableaus of shape 4 to 1, where you just fill 1, 2, 3, 4, 5, 6, 7. You just do this. And to this tableau, you associate two groups, two subgroups of SD, A and B. A is the group of permutations such that you usually say that they preserve rows, right? So they preserve rows. This means that if you apply sigma to each entry, here instead of 1 you put sigma 1, instead of 2 you put sigma 2, and so on, the entries in each row will be the same. In a different order perhaps, but sigma will send 1 to either 1, 2, 3, or 4. 2 will also be one of them, 3 will be one of them, 4 will be one of them. And it doesn't permute entries between different rows. 5 or 6 may stay put or be conjugate, be transposed, but nothing else. And you, of course, B is the same, but for columns. And then you produce two elements called A lambda, which is just the sum of the sigmas in A, B lambda, the alternate sum of the TOS in B. And finally, you can obtain the Specht representation of the dth symmetric group associated to lambda by doing the following. You just do this, just multiply the group algebra. You look at the right ideal generated by this product. And this is H lambda, and I'm seeing this as a representation on the right. Okay, so it's a fact, which I am not going to prove or anything, that this guy is simple representation associated to SD. Okay, this is a quick way to construct it. It has several nice properties, which I will just quote. The one particularly non-obvious one is that if you act on this side by A lambda, B lambda, so you're multiplying, you're looking at what happens with CSD, and you multiply by A lambda and B lambda to the right and to the left. In fact, I want to do more. I want to do this. Okay, so I have mu and lambda, they are different. And then this will provide only two possible answers. This is either a one-dimensional vector space, right? So it's spanned by some vector called, say, V lambda. V lambda is a bad idea. W lambda. If lambda and mu coincide, it's zero otherwise. So this is a nice property of these representations. And there's another property very similar to the Pieri rule, which says the following. This is called the branching rule, but it's essentially not so distant cousin of the Pieri rule. It says, okay, suppose you look at H lambda, right? This is a representation of the group SD, and you look at it as a representation of the group SD minus 1. So of permutations that will only move the first d minus 1 elements and leave d fixed. Now this, since sd minus 1 is semi-simple, this has to decompose as a direct sum of simple representations. So the branching rule says that these representations will appear with multiplicity 1, and even more, they will, or the mu's that appear there will come from lambda by removing a box, right? So the Young tableau of mu is the Young tableau of lambda minus exactly one box. So again, a couple of examples. If I take the representation corresponding to 4 to 1, and I restrict this to S6, I will get a direct sum of some representations of S6, which are F42, 411, and 321. Okay. And now, just like with the Pierre rule, I want to take one example and follow this all the way to the end, right? So I'm going to do successive restrictions until I get something interesting. So let's start with H22. I will restrict it, and I will just get H21. This is the only, so this is simple as a representation of S4 and of S3. When I look at this as a representation of S2, this splits into two direct summands. And then each one of these splits into just restricts to a trivial representation. Okay. So this is telling me that when I restrict H22 all the way to the symmetric group on one element, I get two simple representations, right? But simple representations of the symmetric group of one element have dimension 1 because it's a trivial group and I have to get a trivial representation. So out of this, I am getting that H22 has dimension 2. And what was an easy way to see that, an easier way to seeing that, was saying that each one of these reductions consisted in removing a box from the H22 diagram, right? So for example, in this case, the first box I removed was this one, right? So at step 4, I removed this one. At step 3, no, wait, what I mean is this. Going from here to here, I had to remove this box. Now going from here to here, I had to remove this box. Sorry, this one. Now going from here to here, I had to remove this box. Then I was left with this guy. On the other hand, if I follow the same procedure for the other copy, first I had to remove this guy, of course. Then I had to remove this guy, then this one, then this one. So this proves that the dimension of H22 is the number of standard Young tableau of shape 2, 2, but of course, this is just as well I could have done it with an arbitrary lambda. Okay, so this is telling you, again, more than just the dimension of these spaces. It is telling you that there is a basis of this guy parametrized by standard Young tableau, right? Because when I do this reduction, I am obtaining one particular subspace. So So I just take a generator, and that generator is associated with this standard Young tableau, and the generator of this space I will associate it with this standard Young tableau, and I will get a basis of the full space. So it's more than just a dimension count. I'm doing more than counting the dimension. I'm finding a basis that is parameterized by this standard Young tableau. And this was already known several years ago, but only in Vershik and Okunkov's paper from 2008 were these elements clearly identified. This basis clearly identified. So how do you do that? You consider the following elements inside the group algebra. These are called Jussies-Murphy elements. And you consider the algebra gamma generated by all of them inside the group algebra of the symmetric group. So this turns out to be a very big commutative algebra. All these elements commute among them, they contain the center of the algebra, and they contain a lot more. And the basis, and for each partition lambda, the basis of H lambda parametrized by a standard Young tableau that is the basis obtained by successive restriction to the different copies of the symmetric group is an eigenbasis for the Jussies-Murphy elements. Right, so each one of those vectors will be an eigenvector, simultaneous eigenvector for all elements in my subalgebra gamma. Even more, if I try to compute this, so if I want to know what the eigenvalue here is for the ith Jussies-Murphy element, what I have to do is I have to look in which box you find the number I. You have to look at its x coordinate. And you have to subtract from it its y coordinate. Right, so for example, in the case we were looking at 1, 2, 3, 4 and 1, 2, 3, 4, if you want to know the eigenvalues of the action of Jm1, Jm2, Jm3 and Jm4 on this basis, for 1 I have to look at the position of 1. Its x coordinate is 1, its y coordinate is also 1, so it's corresponding to this vector. Jm1 will act with eigenvalue 0, just multiplication by 0, same here. And for Jm2, you have to look at the position of 2, x coordinate is 1, y coordinate is 0, so you get 1 here, minus 1, 0, and this is minus 1, 1, 0. Now the vectors you get here are known as the content vectors of the tableau, right? This horizontal sequence. And they determine the tableau. So having out of the tableau, you can get the content. Out of the content, you can get the tableau. So it's important that you have to know the order of these vectors, right? They are ordered sequences because the sequences are the same for both these vectors, just that, so the numbers that appear in both content vectors are the same. They're just in a different order. But out of the content vector, you can get back the tableau. So in fact, if I just forget about this restriction process for the h lambdas, and you just give me an h lambda, and you ask me, okay, what's the vector corresponding to 1, 2, 3, 4, to this tableau? I don't need to do a successive restriction process. I can just look at the action of the Jussies-Murphy elements, and I can say, okay, I'm going to diagonalize. I'm going to find an eigenbasis for the Jussies-Murphy elements. And out of the whole eigenbasis, I'm just going to take the one eigenvector with these eigenvalues. And this is going to be this guy here. Okay. So most of this was sort of known in different bits and pieces, but what Vershik and Okunkov did was just put it all together and say, okay, all of these different combinatorics that appear, if you just start from the Jussies-Murphy elements, all the tableau combinatorics come out automatically. If you've never done symmetric group theory, and you don't know where all these tableaus are coming from, you can start by doing this. They give a very reasonable construction, this subalgebra, and they say, and out of this, all the tableau combinatorics arises very easily. So this is something we were very interested in originally. Okay, and now I have to put 2 and 2 together. I have to take my V tensor D, and I want to apply this symmetric group combinatorics to that representation. And to do that, I'm going to use a very old tool known as Schur-Weil duality. So the trick in Schur-Weil duality is to consider V tensor D on the left as a GLN module and on the right as an SD module. How does SD act on a vector here? Well, if you have V1, tensor V2, tensor, and so on, all the way to tensor VD, and you want to act by a permutation sigma, well, you just act on the position of the vectors. Right? So this is V sigma 1, tensor V sigma 2, all the way to V sigma T. And there is a very nice, so why is this called a duality? Because you can see that these permutations belong to the GLN linear endomorphisms of V tensor D. This is very easy. You just, essentially you check. It's by direct inspection. And also by direct inspection, GLN is falls inside the action of GLN, falls inside the endomorphisms in here, right? And the classical result says that this is actually an isomorphism, and this is also an isomorphism. Well, not an isomorphism. That if you look at the enveloping algebra here, this will no longer be injective, but it will be surjective. So if you look at this as a bimodule, the GLN linear morphisms, endomorphisms of this GLN module, are the maps given by the action of the symmetric group. If you look at this as a module over the symmetric group, its morphisms are, these endomorphisms are precisely those that arise from the action of GLN. So this is the duality. Okay, and it's actually not hard to prove, but I'm a bit short on time, so I was planning on giving a 2-line proof, but we can skip that. It's not essential. It's just important that out of this, it follows that when you decompose V tensor D simultaneously as a left GLN module and a right SD module, then you get a decomposition. Of course, it has, as a SD module, it has to decompose as a direct sum of H lambdas because SD is semi-simple. Now, it turns out that whatever comes up here is going to be something that is also indexed by lambdas. Now, it turns out that this, by Schur-Weil duality, this has to be a simple GLV module, GLN, this is G module, right? Okay, I'm gonna do this. So why is that? Because you can take U lambda, because if you want to compute the endomorphisms over SD, this, then this is just the product of the endomorphisms, the linear endomorphisms, the spaces U lambda. Right, and this is because any SD endomorphism has to respect the lambda decomposition, so it can only act on the U lambda part, and it will act on the U lambda part essentially freely, because you can send any vector of H lambda to any vector, and it will just generate the same module. But as we said, this is precisely the image of the enveloping algebra in there. And since U lambda is a simple module over this algebra, the action of G on this will be simple, right? This will be an irreducible module over G because it's an irreducible module over this guy. Okay, so it's an irreducible module and it is indexed by lambda. It would be great if it was isomorphic to the V lambda, right? I have just said it, this lambda index came simply out of the fact that H had a lambda index. So I claim that U lambda is isomorphic to V lambda. And for this, I will show it for my favorite partition for 4-to-1, but then you will see that the proof works perfectly for any other case. So let's just fix lambda to be 4-to-1. And I will define the following notation. I will write I1 bar I2. This will just mean the I1th canonical vector tensor the I2th canonical vector, and so on, all the way to EI7. And these guys will form the monomial basis of V to the tensor D. Right? And this is the basis where I want to write everything in. And also, I want the following notation. I will write I1, I5, I7, I2, I3, I4, I6. I will write something like this. For the image of this guy by B lambda. Right, and by definition, because of who B lambda is, if I take this guy, any vector that looks like this is antisymmetric in the columns. So if I, for example, permute this and this, I get minus the original vector. Right? This is just because of how B lambda acts. This is projection to the subspace where these columns are antisymmetric. So this is just a little bit of notation. Okay. Now, remember that H lambda times C lambda contains exactly one vector and h mu times c lambda contains nothing, right? So if I do u lambda tensor h lambda, sorry, what I mean is if I do v tensor d and multiply by c lambda, I will get a copy of u lambda tensor this one vector and nothing else. This is the one I had called w lambda. So if I can prove that in here there is a highest weight vector of weight lambda, I have proved that u lambda is the unique simple representation with highest weight lambda. But that's not hard to do because in here you will get the element 1, 1, 1, 2, 2, 3. You will get this guy. And I claim that this guy is a v lambda, is a highest weight vector of weight. So that its weight is lambda is clear because its weight is the sum of the weights of all its tensor vectors. So it's 1, 2, 3, 4. It's lambda 1, 4, 2, 1. So this is its weight. This is a vector of weight 4 to 1, so lambda. And I claim that if I multiply this by any upper triangular matrix, I will get 0 out of it. And the way to see it is also very easy. Let me just do an example. So an example of an upper triangular matrix is E1, 2. And what this matrix does is it will act on each one of these vectors by checking if the input is a 2, and it will produce a 1 as an output. And otherwise, you get 0. So E1, 2 of this vector v lambda is the same vector, only one of the 2's has to be changed into a 1. And you have to do it in all possible ways. Like I said, these vectors have antisymmetric columns. And these terms are telling me that these antisymmetric vectors are 0. And the same argument will work if you take, instead of E1, 2, E2, 3, E1, 3, whatever. The action of any upper triangular matrix will turn any of these numbers into a smaller one, and that smaller number already has to appear in the same column. So this shows that I have a highest weight vector of the correct weight, and this implies that u lambda is precisely v lambda. Okay, so I have my decomposition. What I have is an isomorphism here, right? This is v lambda tensor h lambda. And I have used very, very, very little content of the representation theory of SD and G. Okay, the fact that this isomorphism exists uses very little of the representation theory. I used very specific, very small facts that are proved in any basic introduction to the representation theory of GLN and of SD. So this isomorphism sort of comes out of nowhere. Okay, it's just because the action is, just because we have this duality, we have this decomposition. And what I would like to say is that my space VT, the subspace in here, which corresponds to a specific tableau, Remember that at the beginning, what I did is I have a standard Young tableau of shape lambda, and I will associate to it one very specific copy of V lambda inside V tensor D. What I claim is that this is the one that corresponds to V lambda tensor. The corresponding vector, corresponding eigenvector of the Jussies-Murphy element, such that the eigenvalues are given by the content of this tableau T. Okay? And the proof is very simple, right? This is my claim. I claim that this subspace that I defined here is precisely the image through this isomorphism of V lambda, of course it has to be a V lambda, tensor, the one-dimensional space that is parametrized by the tableau T. Right, so these two parametrizations on both sides, the one I described at the beginning and the one given by Vershik and Okunkov, coincide. And this is very easy to do, essentially because you prove it by induction. Again, this case is trivial. So this holds well. Now I want to show that if I know the result for D, it will hold for D plus 1. And here I have to remind you that Ving the vector Vt means that C of SD times Vt will generate a copy of H lambda. C of SD minus 1 times this guy will generate a copy of H lambda minus, where I have just removed the dth box in T, the box that contains the entry D, and lambda minus is the diagram that is left out of that. And then the module spanned by Vt over SD minus 2 is the H lambda minus minus, which I will obtain by removing the boxes that contain D and D minus 1 and so on. Right? So what I am assuming is that Vt is the span. So for tableau T of shape lambda, partition of something, anything up to D, could be less than D. What I'm claiming is that the big space Vt is the span of eigenvectors of Jussies-Murphy 1 all the way to Jussies-Murphy D, such that so Jussies-Murphy I times V is the content, the ith entry of the content of the tableau T times V. So it's a weight space for the Jussies-Murphy elements up to D. Okay? And then the point is just to see that when I do V tensor D tensor V, this will be the direct sum of all the Vt tensor V over tableau with shape lambda, which is a partition of D. And by Schur-Weil decomposition, this is the sum of the U mu H mu. This is partitions of T plus 1. And this is, if I restrict to SD minus 1, so to SD, sorry, I restrict from D plus 1 to SD, I get Vt tensor V, Yeah, so I'm sending this, I get u lambda tensor v, tensor h lambda. Right? And comparing this to restrictions, this is telling me that the only place where this guy can go, where I get the correct lambda, is precisely, I'm making a mess of this, just give me a second. Yes, I want to say that this decomposes as the sum of vt primes with t prime an extra box. Okay. So just a second, my notes are confusing me more than helping here. Yes, okay, so I want to show that all vectors here correspond to, I want to prove this statement for any one of these t primes, right? But if this t prime comes from this tensor product, then I already know that the result holds for these guys, because the action of the symmetric product of the dth symmetric group will depend only on this part. It's the action of the dth plus one Juice's Murphy element that depends on what's happening here. Right? So if the vt prime I'm looking at comes out of this, then it will go that necessarily will go in here. So all I care about is the action of the dth plus one Juice's Murphy element. It has to go this was clear earlier. So I'm taking a copy of these guys in here. It definitely has to satisfy this. I just care about the eigenvalue of the action of the d plus one Juice's Murphy eigenvector, the Juice's Murphy element here. And okay, yes. So I know that this will decompose as just this chunk with t fixed will decompose as the direct sum of vt primes with t prime one extra box from t. So I know precisely where I'm ending up here. I am ending up at, oh, come on. Let me start this diagram again. Okay. Oh, now we have a lot of participants. I want to show this statement by induction. I want to show that the space I labeled by the standard tableau T is the span of the eigenvectors of the Jussies-Murphy elements corresponding to this. I'm assuming I know it all the way up to D. Now I want to do this for D minus 1. So these two guys are equal. And I know that this decomposes as Vt tensor V, where T is all standard tableau, shape lambda. And this other thing, by Schur-Weil duality, I know that this decomposes as a direct sum of V lambda tensor H lambda. Now, fix something here, fix a Vt prime. So this fixes, so what I want to say is that if I restrict this to D, this is why I should practice more my talks. Oh.
¿Qué te parece si nos contás un poco cuál es tu problema?
Dale. Yo lo que quiero probar es lo siguiente, ¿no? Yo sé que...
So probably in English, I apologize.
Right. Sorry.
Because I raised the question in Spanish.
Yes. So what I want to do is the following. I know that these two guys will decompose on the one hand like this, because I proved it at the start. And on the other hand, that by Schur-Weil duality, I have decompositions like this. This is partitions on D plus 1. And this is, let's do mu for this. And this is partitions for D. And there's a tensor V here. And what I know is that I know precisely where this particular guy will end up here. This Vt here will end up as the vectors of the form V sub t, so the ones that already have the eigenvalues that I want, tensor the whole thing, tensor V lambda tensor V. And now what I want to prove is that if a Vt prime came from decomposing this by doing the Pieri rule, then it will end up here in the only copy of V shape of T prime, tensor V of T prime. So the only, and to prove this, all I have to do is I have to show that vectors in here have the correct eigenvalues when I apply the Jussies-Murphy elements. And since they come from this part of the module, I know what the action of the first V Jussies-Murphy elements is, and I know that it is the one I want. And since I know where Vt prime is ending up here, so it's ending up here, Okay, so there's a technicality here I am missing at the moment, but essentially when I look at the possible eigenvalues of the Jussies-Murphy elements that appear in here, they will correspond to tableaus of the shape of T, right? So to tableaus like 1, 2, whatever. And then one more. Then I have to diagonalize the last Jussies-Murphy element, the T plus 1. And what I'm claiming is that at each step, if I know the shape T prime, then I know exactly where I added the D plus 1 box. And this fixes the action of the Jussies-Murphy element. So okay, yeah, no, I got it. My apologies. So let's start again. Sorry, last time. I am looking at a vector V inside this particular T prime, right? And I am looking at its image through Schur-Weil duality here. I want to know that it has the correct eigenvalues for the action of the Jussies-Murphy elements. And for that, what I have to do is I have to check what module it spans over the df symmetric group, over the d minus 1 symmetric group, over the d minus 2 symmetric group, and so on. So this vector v, when I map it to the other side, it has to end up in something, in a copy of this module here, right? So it has to end up in a copy of v sub shape of T prime. And this has to lie, so it has to end up somewhere here. So when I look at the image of the vector v and I apply the action of the symmetric group SD, it can only generate a copy of this representation. So if you call this map phi, phi v times this has to be isomorphic to the representation associated to the shape of T prime. Now, if you look at phi v times CSD minus 1, I claim that this will be this representation. Sorry, this is D plus 1 and this is just D. And this is just because this vector here belonged to this space here. And because it has the correct Jussies-Murphy eigenvalues, phi v times CSD minus 1 will be isomorphic to H of the shape of T, except where I removed the df entry, and so on. So phi v, the representation that it generates over the symmetric group of R elements will correspond to the representation that you get by removing all boxes up to r+1. The first part comes from the fact that I took it from this particular representations. Bye, Claude, thanks for the inner peace. Okay, so this spans this representation because it lies in here. And all these other cases just follow from the fact that this one tableau came from this tensor product through the Pieri rule. So the fact that it restricts to the correct representations is telling me that the eigenvalues of the Jussies-Murphy elements is fixed. And it is fixed as the contents of this guy. Because remember, T is just T prime with T+1 removed. This is how I got it. Okay. So by knowing all these restricted representations, I know the corresponding Jussies-Murphy eigenvalues. And by that, I know the corresponding tableau to that. And just this construction is telling me that tableau is T prime. Right? So maybe I probably lost everybody in the middle, but in here there is a proof that V sub T is precisely the space of CT eigenvalues for the Jussies-Murphy elements. Okay, so this answers question number 1, which was, can I give a characterization of this subspace, which does not depend on me doing all the intermediate steps of the tensoring. I just have to look at the action of the Jussies-Murphy elements on V tensor D, diagonalize it, and look for a specific set of eigenvectors. In fact, this guy is a weight space for the eigenvalue decomposition of the Jussies-Murphy elements. That gives me 1. So that's an answer for question 1. Question 2 was asking for all the highest weight vectors in all the VTs, at least. So I got 1 highest weight vector, which is the one associated to this tableau I mentioned here, when I proved that VT was a highest weight representation and that this was the highest weight vector. This is telling me at least 1 highest weight vectors in one of the VT, in the VT associated where T is this particular tableau, the standard tableau. What about the others? Well, part of Vershik and Okunkov's construction is that this eigenbasis is sort of recursive. There are explicit coefficients for the action on this basis. And you can, with some work, construct them recursively. So that's annoying. That part is still recursive, but you can recursively construct the highest weight vectors in all the VTs once you know the highest weight vector in the first, in the VT associated to the standard tableau. So highest weight vectors are known up to computations. The first is obtained the first one is obtained very easily. You just take a very obvious monomial and you anti-symmetrize it. That's the obvious example. And the other ones are just obtained by applying certain nice elements in the group algebra. Probably complicated elements, but manageable. Still, we have a program with Joanna to actually compute them, and it takes quite a while to actually produce them. So, but I would say that problem is sort of solved. Now, the third problem I mentioned, translates into finding this isomorphism explicitly, right? Give me an explicit isomorphism for the Schur-Weil duality. And this is surprisingly hard, considering that we got it almost for free. That the Schur-Weil isomorphism exists is almost abstract nonsense, but making it explicit is very, very hard. For that, you need a basis here. You have the monomial basis. You have the basis that Vershik and Okunkov constructed here, and this, they call it the Gelfand-Tsetlin basis. And they call it the Gelfand-Tsetlin basis because the process they use to build this basis is a mimic of a process that Gelfand and Tsetlin used to get the Gelfand-Tsetlin basis here. So there's a Gelfand-Tsetlin basis for representations of GLN. It's a very complicated basis. It's very hard to pin down. But if we manage to find this isomorphism explicitly, we would manage to understand it in terms of the monomial basis here. And this is how we started thinking about this stuff. We wanted to understand this basis and this basis. We thought, well, they both appear in the Schur-Weil duality. What if we just put them inside? What if we just put them through the machinery of Schur-Weil? And that ends up being about finding this isomorphism explicitly in this basis. We are ongoingly working on that. And I am interested more generally, so a couple of things that should come out of this. I'm interested in Gelfand-Tsetlin basis for more general types of representations. This is something that should tell us, should give us more experience on how Gelfand-Tsetlin bases work in two of the more well understood contexts. But still, if we had this isomorphism, we would be able to compute a Gelfand-Tsetlin basis for this tensor product. And nobody knows how to compute tensors of Gelfand-Tsetlin basis. This is another of the motivating problems. I want to be able to compute a Gelfand-Tsetlin basis out of this. So a Gelfand-Tsetlin version of the PRE rule would be something I would be very happy with. One thing that Joanna likes to emphasize is that this particular basis that we built, the one that Vershik and Okunkov mentioned, is done through restriction to very particular copies of SD, SD-1, SD-2, etc. What if we take different restrictions? What if we take a different path? What if we build our tableau according to different conventions? Well, the Schur-Weil duality still exists, and this isomorphism is practically fixed. This is a very rigid thing, because since this here is a semi-simple representation of GLN SD. So the Schur-Weil isomorphism is quite fixed. You cannot change it except up to constants for each fixed lambda. But if you change the restrictions of the symmetric groups, it's going to be a whole different combinatorial game. But you can probably follow it explicitly through this construction. So it's interesting to explore these different processes. And the Gelfand-Tsetlin basis for GLN is also constructed through a very specific restriction procedure from GLN, GLN-1, etc. I'm also interested in switching that up and finding different restriction paths and to see what this brings up here. Okay, sorry for that middle interruption. I'm done. Thank you very much.
Thank you, Pablo.
Francisco, Gracias. Anne, thank you. Joanna, thank you. Questions? Javi, te veo desmuteado.
¿Me ves? No, ¿me escuchás?
Te escucho.
Hola, perdón, estuve un poco distraído porque no estoy en casa. Y no, tal vez lo dijiste ya, pero como que a partir de que n, de que d se complica, me imagino que es un d muy chico, pero no sé, ¿se puede ir viendo alguna cosita o los números son suficientemente chicos como para que no te den intuición de nada? Porque...
So this is a very good question. I'm going to repeat it in English. He's asking how
sorry.
big can, don't worry, how big do n and d have to be until this gets complicated? And the answer is very quickly. If you do n equals 3 and d equals 3, then you can sort of do it, sort of. But I have this running program. I forgot to start it, and I don't want to start again. But we have this running program for n equal to 3 and d equal to 5. So C3 tensor 5, and it takes the computer more than 2 minutes to compute all these things. So that should give you an idea, and it just grows exponentially. So it's exponentially,
But
so you can do quite a lot of things to just pin down what you're computing more easily. You can, but that means you have to really get into the theory, and you know where to look for certain things and where not to look. But so if you just try to brute force it, as soon as n is larger than 3 and d is larger than 5, you get a really huge thing. Like I could not compute the case 3-3 by hand. Or maybe I could with a lot of time. But I think this is the one thing we spent months discussing over and over again, Joanna.
Can you hear me actually?
Yeah.
Okay. Sorry, I seem to have dropped out a little bit in the middle. Yeah, it's so there's still room for improvements, I think, but also when, as Pablo was saying, when you're doing these computations by hand, this is already extremely tedious for the case that n is equal to 3. And yeah, maybe so let me add one thing to it. So if you have like somehow n very large, then the theory is somehow nicer, because I mean, as Pablo was writing down the Schur duality somehow, so the picture gets a little bit disturbed if the n is somehow so small that the branching will be a bit will be a bit broken, so to say. But I think for explicit computations, as soon as n gets a bit bigger, I mean, for d equal to 2, that's always very easy, but then with growing and more interesting d, this is yet to be optimized. So currently the program that we've written is mainly just showing that you can do it with the means of SAHHAS, which was another obstruction in writing this. But yeah, it needs to be improved. On the other hand, oh no, so yeah, exactly, yeah. On the other hand, so one thing that would be also really nice from experiments where we just let the program run for some time, we hope to be able to also derive some explicit formulas for the coefficients, where we don't have to go through these computations with these content vectors and the Gelfand-Tsetlin eigenvectors and the correct weight spaces and so on, but where we can just find some explicit formula for the coefficients.
And I mean, this is in the end getting an explicit version of this
Yes.
isomorphism. So this isomorphism packs up lots of things. So getting an explicit version is unpacking them. And one of them is this: you get explicit formulas for this, for these vectors, which is, well, if you ask everyone, they will tell you, yeah, sure, you can do it. Then nobody can do it.
Of course.
Yeah, it's an area where I think the theory is very, very well explored, but then the any explicit computations are quite hard to obtain, even though everything is there.
One very standard answer you would get, in fact, I think this is the answer I gave Joanna the first time this problem came up, is that, oh, you probably just have to look at this, at some correct vector, and just apply some Schur symmetrizer, right? Like the symmetrizer, anti-symmetrizer I drew at some point, a lambda, v lambda for some adequate lambda. And I asked a couple of people, and they also gave me this answer, and this is wrong. This doesn't work because these guys are idempotents, but not orthogonal idempotents inside the group algebra. So this is something that sometimes takes people by surprise. And in fact, we found a reference for a proof that they practically never are, and it's a very recent paper. So these are the sort of details that got lost while we were building, I don't know, Kazhdan-Lustig theory.
Thank you. That's a lot.
Yes.
Okay.
So how, actually, I have a question to also the other audience. So how well known is Schur duality to you? Is it also something that you encounter and use often, or is it not so prominent for you?
For me, it's something that I have heard of, but maybe I can, maybe I heard something about Schur and while that wasn't that, I don't know. but of course, that is not something that I see frequently.
Yeah, thanks.
I think that's general for us in the Argentina, Uruguay region. It's like something not too often mentioned.
Yeah.
Like
Yeah,
when I first got to talking to all these people that were working on representation of Lie algebras, I realized I had like this gaping hole in my knowledge because I had no idea what Schur duality was.
Yeah. It feels like Schur duality people and Gelfand-Tsetlin people have not talked enough in the past century.
Only 80 years for, no,
Yeah.
70 years for Gelfand-Tsetlin.
That's true. Right.
Okay.